Good afternoon, everyone, and welcome to the College of Engineering virtual Brown Bag series. I'm Gautam Das. I'm the Associate Dean for Research, College of Engineering, and I'll be the host of today's presentations. We have today two professors from the college. The title of their topic is going to be A Peek into the Future of 3D Printing. I will introduce the two professors in a minute, but I just first wanted to let you know that this presentation will run for about 40-45 minutes, and then after that, we will open up to question answers. There is a Q&A widget on your screen on the Teams windows, which you can use to type in your questions either during the talk or after the talk is over, and it'll be my business to read them out to the presenters, and hopefully we'll have an interesting discussion towards the end. So very fascinating topic. Our presenters for today are Professor Amir Wang, Assistant Professor in Industrial Engineering today, and Amir Ameri, Assistant Professor in Mechanical and Aerospace Department. And the topic is really on 3D printing, which I'll give a brief abstract description of it. It emerged in the late 1980s, and it's been changing our lives daily. How we design and fabricate new parts, how we manufacture parts, how we dispose of used parts, and so on. And because of the unique layer-by-layer production methods, it has brought numerous exciting opportunities for future of manufacturing. Make-to-order, on-demand production, green manufacturing, circular economy-driven manufacturing, smart materials, and so on. So obviously, they will fill it up with a lot of details in their presentation, so I will not get into the details here. Dr. Amir Wang is an assistant professor at the Department of Industrial Manufacturing and Systems Engineering, and she's the director of the Sustainable and Intelligent Manufacturing Lab, also known as the Smas Lab. She has a PhD degree in Industrial Engineering and OR from the University of Illinois at Chicago. Dr. Yang's research is focused on sustainability practices in additive manufacturing, from design, production, distribution, use, to end of life towards green and smart manufacturing. Dr. Yang has also been devoting her time to advising students, serving the scientific community, K-12 outreach, and workforce development for future manufacturing. Our second speaker, by the way, both of them will be sharing the presentation today. Dr. Amir Ameri is an assistant professor in the Department of Mechanical and Aerospace Engineering and the director of Advanced Materials Engineering Research and Innovation Lab, also known as the Ameri Lab, which incidentally is his name, at the university. Prior to joining UTA in 2019, he was additive manufacturing design applications engineer at Voc company in Houston. I'm sorry if I got that wrong. He also spent 5 years as a graduate student in the Dynamics and Smart Systems Lab at the University of Toledo. He is a recognized expert in the field of SMAs. He will tell you more about what SMAs are, and I don't want to take that opportunity myself, and has led numerous projects to develop high-performance engineering components for applications in space, aerospace, automotive, and oil and gas. His research emphasis is on fabrication of structural and functional NITI-based alloys. Again, he will expand more on what these alloys are. Advanced materials characterization, machine learning, and process optimization. He's a prolific researcher, published over 50 papers, 28 of them are peer-reviewed journal articles. So with this introduction, I'd like to invite the speakers to start their presentations, and I look forward to an exciting 40 minutes or thereabouts. You're muted, Amir.
All right, can you hear me?
Yes.
Perfect. Thank you so much, Dr. Das, for the introduction, and hello everyone. This is Amir Ameri from MA department. Today I'm here with you all to talk about my recent research on the topic of metal additive manufacturing. As a brief introduction, as also Dr. Doss mentioned, I earned my PhD in 2018 and joined UTA in 2019. My research area is in the additive manufacturing of functional and structural alloy with a specific focus on shape memory alloys. Now I'm asking my colleague, Dr. Yang, to also introduce herself and continue with a brief introduction to the additive manufacturing. Dr. Yang.
Hi, everyone. I'm Emma Yang. I'm an assistant professor from industrial engineering. It is my great pleasure to join Dr. Ameri to present you this virtual brown bag talk on 3D printing. And thank you all for attending this talk. So I would like to start today's talk with one simple question. How do you usually buy your shoes? Well, personally, I usually prefer to going into the stores. Like I like going to the stores, trying them on and comparing maybe different brands, different prices, etc. Well, now after COVID, I know more people have been starting to shop online, which actually provided a more efficient way of shopping. So now with 3D printing, what can be the potential way for people to purchase their shoes? Now let's look at Adidas Speed Factory in Germany as an example. Well, they offer high level of customization, meaning you can design your own shoes that fit your personal needs, whether you are a professional athlete who needs a pair of, let's say, running shoes, or if you are a patient needing some shoe insoles for your physical therapy. You can customize your shoes and they will make sure the shoes can satisfy your needs. Well, you can choose to send the 3D scanning data of your feet, or you can actually go into the store and let them collect data. Then they can fabricate your shoes and then they can actually run simulation. For example, if you are a professional soccer player, they can use a robot arm to simulate the movement of kicking a soccer ball and see if the shoes can actually take the kick, but also protect your foot. And they can also do the simulation in different environments to cold or hot. They can customize shoes and shoes insoles. Well, I know for a fact that Adidas actually subcontracts their shoe insole orders to some small 3D printing companies like Carbon 3D. And they also offer like machine kneading and manual kneading to make sure you can achieve the functionality you're looking for and also the shoes look nice. So with 3D printing providing high level of customization, we now have an entirely new option for buying a pair of shoes. Now the next question is, how do we build a house? Well, I actually just bought my first house a couple months ago. It's a new construction. Well, it's still dirt. They haven't started anything yet. I wouldn't say I'm an expert, but like I have been starting to get to know a little bit more about building a house. So traditionally, to build a house, what you need to buy the land, right? And then you need to get all the electricity, the water in. You need to design the floor plan. You need to build the foundation, framing, all the major systems. And of course, you need to do the interior and exterior finishes. So this whole process usually takes a couple months to a year, depending on the availability of raw materials or labor, right? So now with 3D printing, how are people building houses? So at Mexico, this 2-bedroom new house was 3D printed in about 24 hours, and they were built for low-income residents. And this one at Italy, this small house was 3D printed in about a couple of days, and they were using mud and waste byproducts. And now let's look at Texas. So this is in Austin, Texas. The local developer and the construction technology company, they 3D printed this house in a few hours. And they actually used concrete that's designed to cope with extreme weather. And this house were for people who were formerly homeless. And you know what? These houses were actually unharmed during the snowstorm back in February. That's really refreshing news because my apartment was flooded and they just fixed everything like a few weeks ago. So this 3D printed house was actually unharmed during the snowstorm. Now, customizing shoes and building houses using 3D printing in a few hours. They are just two examples of how 3D printing is actually changing our lives. 3D printing, or we call it additive manufacturing, is a process of joining materials layer by layer to make 3D objects, as opposed to traditional subtractive manufacturing. 3D printing was invented back in the 1980s for making prototypes. And then later on, with the advancements in new materials, new control algorithms, and new technologies, 3D printing has been used to fabricate tools, fixtures, and now functional products. The global 3D printing market has been rapidly increasing, and that leads to applications in a wide range of domains, such as aerospace, automobile, medical devices, etc. A lot of companies have been expanding their service to 3D printing, like Amazon, Home Depot, and Autodesk. And there are some new 3D printing companies emerging as well, like 3D Systems, Stratasys. Well, at UTA, we have a wide range of different 3D printers. For example, I know at Dr. Ameri's lab, they have a laser powder bed fusion printer that uses metal powders. And at my Sigma lab, we have Selective laser sintering printer that prints nylon. And we have stereolithography that deals with photosensitive liquid resin. And we also have a dual nozzle material extrusion printer that prints like thermoplastics like ABS or PLA. And a lot of other labs at UTA have different 3D printers. For example, I know in mechanical engineering department, Dr. Taylor has a multi-material jetting printer, right? And the UTA Fab Lab, which is on the first floor of the library, I think they have like almost 10 FDM printers. So UTA definitely provides students with easy access to different 3D printers. So if you are interested in doing some research in 3D printing or outreach, or you just simply want to know more about 3D printing, please feel free to reach out to me or Dr. Ameri. We will be more than happy to talk to you. So today in this talk, Dr. Ameri and I will be focusing on two research topics. The first one will be on smart materials. Dr. Ameri will start by talking about how to fabricate smart materials using an inexpensive approach. And then I will focus on green manufacturing. We're gonna explore if 3D printing is actually environmentally friendly.
All right. Thank you so much. Let me share my screen. All right. Can you see my screen?
Yes.
Yes.
All right. Thank you so much. All right. Thanks, Dr. Yang, for a very exciting introduction about the additive manufacturing technique. Now, I would like to start talking about selective laser melting, which is one of the most common powder bed-based additive manufacturing techniques for the fabrication of metal components. With selective laser melting, or SLM technique, it is possible to fabricate parts with complex geometry with high precision, such as lattice structure, curved component, or parts with overhangs. Here at UTA, we have an EOS M290. If I find that laser, okay. Here at UTA, as you can see here, we have an EOS M290 SLM machine that is equipped with a 400-watt laser, fiber laser, which allows us to fabricate parts from different types of powder for a variety of applications such as aerospace, defense, biomedicine, etc. There are several common powder materials by which you can simply fabricate part using SLM machine at UTA, and the reason is that the process parameters have already been optimized by the manufacturer. The material available at UTA, they are stainless steel, steel-based alloys such as 316, nickel superalloys, Inconel 718, 625, titanium grade 5 for the biomedical application, as well as aluminum alloys. So, right. Now I want to talk about some other materials that are of great interest, but their process parameters for additive manufacturing have not been optimized yet for a high-end application. To name a few, the materials that are of great interest include nickel titanium or nitinol-based shape memory alloys, refractory metals, magnesium-based alloys, and composites. Before talking about the procedure of process parameter optimization in additive manufacturing or the SLM for a specific alloy, I would like to briefly talk about SLM technique in general. First of all, an ingot of the desirable alloy needs to be gas atomized to produce the powder. Then the CAD file of the component needs to be segmented into layers, and appropriate process parameter need to be assigned to the layer. The next step is the procedure of SLM fabrication, as you can see here. During the fabrication procedure, a layer of the powder alloy is deposited. This is followed by selective laser melting of the laser based on the defined CAD file geometry. Once the melting and solidification of the layer are done, the building platform drops down by the thickness of the height of the layer. This procedure would be repeated, as you can see here, until the entire part is ready or fabricated. As the final step, the part has to be separated from the base plate either through removing the support or either EDM cutter. Now I would like to talk about the procedure of processing parameters optimization that we perform in our lab for a very interesting material called nitinol or NITI, shape memory alloy. The term SMA or shape memory alloy might be familiar to you. As you can see in this video, on the top right, SMA can undergo significant amount of strain, up to 8%. Just for your information, the stainless steel is about 1.5%. And it can be deformed before it enters to the plastic region. That is why we call this material superelastic alloy as well. One major challenge with optimization of processing parameter for additive manufacturing nitinol is that we need to make sure the material would show superelasticity right after the fabrication without requiring any heat treatment or post-processing. Before this work that I'm gonna talk about it, the highest achieved superelasticity in the literature for the as fabricated part was only 2%. Very close to the stainless steel. Well, let me talk about the most important parameters in the optimization that have to be tuned during the procedure of the optimization. These parameters for additive manufacturing or SLMs include laser power, which is the power of the laser, scanning speed, which is the speed of the laser beam travel during the fabrication, hatch spacing, which is the distance between neighboring laser tracks, and layer thickness. There is a well-known term that relate between these process parameter, which is called energy input. Energy input is equal to the power, as you can see here, divided by the scan speed, hatch space, and layer thickness. The very first step in optimizing process parameter is looking at impurity pickup, density, and also the surface quality of the fabricated part. We observe, as you can see here in this graph, we observe higher density with higher energy input, which was desirable, but also higher impurity pickup, which was undesirable. Per the ASTM standard, we selected a range for the process parameter that met the requirement of high density, allowable impurity pickup based on the rules for or standard for the biomedical application, and good surface quality, all desirable stuff for biomedical application. The next step was to further narrow down the parameter in a way to ensure the as fabricated part demonstrates superelasticity. Well, it is well known that superelasticity can be achieved through modification in the microstructure and texture of the fabricated part. In regard to the microstructure, it has to be in a way to provide epitaxial growth, I mean appropriate level of remelting between each layer. As you can see here, if the energy is not enough for the fabrication, the layer would not be connected to the previous layer. On the other hand, if the energy is too much or excessive, there would be overheat which intensifies residual stresses and causes significant grain growth, which are undesirable in general. In regard to the texture, it is well known that the presence of 001 texture can significantly improve the superelasticity when compared with polycrystalline structure. As you can see here in this figure, level of strain recovery is about 5% for single crystal conventional material, while it is only 3% for the same material, but in the polycrystalline mode for the conventional, again, fabricated part of nickel titanium. Therefore, we performed design of experiment and try to achieve a set of parameters that result in epitaxial growth as well as 001 texture. After SEM and EBSD analysis of all specimens, we were able to obtain a set of parameters that result in epitaxial growth and produce single crystal. The hypothesis here was that such microstructure, as you can see here, and as well as the texture, result in perfect superelasticity. Therefore, the next step was to test this hypothesis. Okay, to testing and doing the mechanical performance analysis. So, in this slide, I would like to show the level of superelasticity of this newly optimized specimen versus that for the state of the art in the literature. As you can see here, in the red line, demonstrate the stress-strain curve of our newly optimized specimen during loading and unloading of the part. Interestingly, for the first time, 6.5% superelasticity was achieved in this specimen without any kind of post-processing heat treatment. On the other hand, the as fabricated SLM NITI samples in the literature demonstrate almost no superelasticity, and that is why the standard of the care is to perform post-processing heat treatment on the as-fabricated samples to create desirable level of superelasticity as well as enhance the strength of the material by inducing more Ni-rich precipitate. Anyway, post-process heat treatment should be avoided as they involve extra time, costs, as well as labor training, and some other associated costs. By the way, even with post-process heat treatment, the highest achieved superelasticity in the literature was only 4.3%, which is absolutely lower than that was seen in over newly optimized specimen. Okay. While this set of process parameters result in perfect superelasticity, both in tension and compression, we figured that the tensile strength of all specimens was significantly lower than of compressive strength, as you can see here. I should mention that this major issue or this drawback is not only associated with the SLM fabricated nitinol, but also observed in all fabricated specimens with different material. Therefore, we started to identify the roots for early failure in tensile testing specifically, and provide some solution to address this issue. Our first hypothesis was that the layer-based feature of SLM specimen result in such an early failure. Therefore, we decided to study the influence of building orientation and scan strategy with the aim of minimizing the adverse influence of layer-wise fabrication. To this aim, we first fabricated NITI sample using different build orientation, as you can see here, as well as different scanning strategy. In the figure presented on the left, you can see the building orientation we consider in this study. For the vertical samples, the load direction as shown was supposed to be perpendicular to each layer. However, for the horizontal specimen, the load direction was considered to be parallel to each layer. In the figure presented on the right, the two employed scanning strategies are also presented. As you can see here, we could change the orientation between each laser track and loading direction. Noteworthy, the newly optimized process parameters were used to fabricate for the fabrication of these specimens. As it can be seen in this slide, it was found that the part processed horizontally with scan strategy of alternating 0-90 degree resulted in the highest mechanical strength. By the way, we found that the influence of the building direction, I mean horizontal or the vertical one, was significantly higher. It was significantly higher than that of scanning strategy. For the specimen built vertically, when we look at the SEM image at the failure, we observe that the type of the failure was interlayer failure. On the other hand, in the case of horizontal fabricated specimen, such failure was not observed, and that is why higher strength was observed. By the way, although relatively higher strength was achieved, there was still room for improvement, and we decided to further investigate the microstructure and find other routes for early failure. Therefore, we decided to do a comprehensive study to evaluate the spatial microstructure properties of the SLM fabricated NITI specimens. Before this study, all the available works in the literature were limited to local microstructure analysis rather than spatial one. We observe significant variation in the microstructure of the specimen when comparing the area near the surface and the area away from the surface. For example, for the area away from the surface, we observe large epitaxial grain, elongated melt pool, and formation minor brittle phases as well. However, when looking into the area near the surface, we observe refined grain, interconnected melt pools, significant number of brittle precipitates, as well as unmelted powder together with cracks, as you can see here. Okay, so here we perform further analysis on the composition and hardness across the cross-section of the specimen 2, and we confirm that brittle precipitates are higher near the surface. Also, as expected, we observe lower hardness value for the area near the surface compared to the middle region. Our hypothesis was that the area near the surface undergo additional convection mode, and that is why the cooling rate at the surface area are higher. In another, I can say in another word, the input energy delivered to the area near the surface is lower than the middle region, as it's shown in this picture as well. And that is why we see more crack, melted powder, irregular melt pools, and maybe refined grains. As a potential solution, we decided to consider a border with an offset from the main part during the fabrication for this study. Our aim was to control the convection heat transfer occur near the surface area. So this position. So by considering this border as it presented here. So our preliminary results demonstrated that adding a border with a gap of about 0.5 millimeter significantly controlled the microstructure variation in SLM fabricated nitinol parts. For example, the sample processed by a broader demonstrated larger epitaxial, we can say equiax grain and more intense melt pools. The future direction on this topic is to further optimize the gap between the border and the main parts and perform mechanical and fatigue tests to obtain the level of improvement in the mechanical strength of as fabricated superelastic nitinol. The result of this study will definitely open new doors for the design and fabrication of high-strength SLM component, which would revolutionize the field of additive manufacturing of SMA or shape memory alloys. Well, I'm done with the presenting my work, and I'm asking my colleague, Dr. Yang, to continue talking about her research on the topic of green manufacturing.
Thank you, Dr. Mary. I think shape memory alloys are very interesting. So the second part of this talk, we're going to focus on the sustainability of 3D printing. So this part of my research, we're going to be focusing on environmental, economic, and social aspects of the sustainability. And it was previously sponsored by National Science Foundation and Energy Department of Energy. We published more than 8 journal papers and some conference papers, but today, because of the limited time, I will only share with you some part of this project and some interesting results. So first, let's look at the process we're going to focus on and why. So this process is called stereolithography. It's a mouthful. I have been using this terminology for like more than 6 years, and I still have trouble pronouncing it. Anyway, let's call it SLA, or some people call it SL process. So with this process, we deal with photosensitive liquid resin, like the yellow colored liquid there. That's our raw material. So we are going to actually build solid parts from that liquid using this technology. So what we do is, well, we have a control computer. We set up the printing, meaning we select the values of some controllable parameters. We send that information to the components of the machine. We use the projector to project the images of each layer to the build platform, and we solidify that layer with UV light. And then we repeat this process layer by layer until we finish the entire production of the part. So why do we choose this process to evaluate the sustainability? Well, first, because it has multiple electricity consumers, and we have some parameters that are associated with them that we can control. So that gives us opportunity to change the energy consumption. Second, the raw material we use here, this photosensitive liquid resin, is VOC coated. What that means, even without 3D printing, that resin can possibly have VOC emissions. Sorry, VOC stands for volatile organic compound. And that's not good for human health. So it's very important to understand how much VOC emission is caused by 3D printing and what we can do to improve the process to reduce or even eliminate the potential human health risks. Last but not the least, one unique thing about this projection-based SLA process is that the printing time does not necessarily change with increasing number of parts. Meaning you might have the same printing time when you print one part versus you print 3 same parts. So that indicates great potential for reducing cost per part. So basically, that's why we decided to focus on this process for sustainability evaluation and for exploring opportunities to enhance the sustainability of 3D printing. So first, we decided to look at energy consumption. Well, this part is very preliminary work. Basically, what we did is we built the mathematical model to estimate the energy consumption. And then we validated that model by comparing the calculated results with experimentally measured results. And the prediction error of our model turned out to be less than 12%. Which is possibly caused by the low level of accuracy of our power meter. Like back then, I used a normal power meter, and I had to manually write down the readings. So that can cause some inaccuracies. But later on, in another energy consumption study, we actually used a more advanced power meter, which has the automatic data logging function. So that actually increased the accuracy. So then based on this model, we performed optimization, and the result actually suggests that we can potentially reduce the energy consumption by around 50% by changing the values of these parameters. I mean, this is a no-brainer because you change the height of each layer, then you change the total printing time. Well, of course, you're going to end up with different energy consumption, right? But the tricky thing here is how to make sure we still have good fabrication quality. Because in my opinion, like any attempts to reduce energy, reduce cost, reduce emission without considering the quality is meaningless. So we also looked at the quality of parts fabricated with optimized parameter We actually found out that using the optimal parameters, we didn't sacrifice the surface quality. But the thing is, here, this is pure experimental. We didn't have the capability of actually estimating or predicting the fabrication quality. So we were actually able to do that later. I'm gonna talk about that later in a few minutes. So this is energy consumption. Next, we looked at the VOC emission. What we did is we built the mathematical model. So in this model, we have two emission sources. One is the emission because of the volatilization, meaning even when you don't 3D print, you just have that raw material sitting in your lab, VOC will escape from that material. The second part is a VOC actually caused by 3D printing. For example, during printing, the built platform moves in and out of the material tank. That disturbance will facilitate the process of volatilization. Also, during printing, the temperature is going to increase, and that can cause additional emission as well. So we validated this model through experiments using real-time VOC monitor. Well, we did like multiple experiments for different materials, for different production scales to validate our model. And the model turns out to have around 14% error. And next, let's look at one of the experiments. I want to show you this plot. So the vertical is VOC concentration, the emission level. The horizontal is time. Now, based on time, we divided the entire experiment into 3 stages. The first one, pre-processing stage, where we were just setting up the machine, prepare for the printing. The second stage is the actual printing, where the machine just fabricates a part. And the third one is post-processing stage, where the printing is finished and we just retrieve the part and do some post-processing. So one interesting thing you can see here is this very evident peak right after we finish the printing. Well, during the measurements, of course, I wasn't aware of this happening, but later on when I saw the results, it actually made sense to me. Because after printing, I opened up the machine cover and took the part out. So I think what happened was that during printing, actually a lot of VOCs emitted from the resin, but they were trapped inside the machine because we have a sealed machine cover. And then when I opened up the machine cover, those VOCs were just suddenly released, causing this peak. So next, we are interested to see if this level of emission will be harmful to people. Well, the reason why we are particularly interested in this is because this type of desktop small-sized 3D printers are often used in universities, high schools for educational purposes, and they are also used in like hospitals or medical facilities to fabricate small medical devices. Students and patients, they are all vulnerable groups. So it's very important to make sure that the emissions from these 3D printers will not cause any health concerns. So after the evaluation, our results show that there's no cancer-related risks, but there are definitely some non-cancer risks like skin irritation, lung problem. So the next step here is, what can we do to reduce that emission and make the printer more environmentally friendly? Well, the commercial method is just to add a machine cover, which has been proven to be not that effective. So we tested 2 methods. One is to use titanium dioxide to oxidize the VOCs, and the other one is to use activated carbon to absorb the VOC. Both methods turn out to have the ability of reducing the emission level by a significant amount. And we actually built a prototype that used both of these 2 strategies and also adopts the optimized parameters that we selected in the energy consumption study. Well, interesting news is that earlier last year, 2020, a company, I remember it's 3D Systems, but I'm not sure. They had a new 3D printer. One of the features that they say about that printer was actually the printer was equipped with VOC emission filters. So I definitely see that companies have been starting to care more about the potential emissions from the 3D printers and what they can do to make the 3D printers more environmentally friendly. So that's energy consumption and process emission. Next, I would like to focus on how to reduce the cost per part. Now, usually we have 3 different layouts for production. One-off production, where we just print one part each time. Non-mixed production, where we have multiple parts, but they all have the same geometry. And also mixed production, where we have multiple parts and they have different geometries. So traditionally in literature, most people are focusing on one-off production or non-mixed batch production, because it's easier to calculate their cost. So what we did here is we built a cost model that is capable of quantifying cost for all 3 different layouts. And based on that, we formulated an optimization problem. So our optimization problem, our objective here is to reduce the cost. But at the same time, we have to make sure we can achieve the desired fabrication quality and make sure we can achieve the desired production throughput. So here you see the formula for surface roughness is complicated. Basically, we had to do a separate study focusing on surface roughness modeling. So the way we modeled the surface roughness is based on staircase arrows. You can see if you print this part with 4 layers, you can see there's a lot of voids here, and that's significant defect. Now, if you increase the number of layers, that defect becomes less significant, but you can still see the staircase arrows. Now, if you further increase the number of layers, that defects becomes less significant, but if you use a microscope, you can still see those staircase arrows. So what we did here is we use this surface profile to represent the actual staircase arrows. And we were able to get the mathematical representation of this profile, and then we transform the coordinate system back to the actual surface, and we were able to build a model for calculating the surface roughness. And then we use the microscope to actually look at the surface profile, and we observed staircase arrows. And then we used this geometry. This is unique because it has different surfaces, like they have multiple surfaces with different angles, so that we can validate our model for different angled surfaces. And we also compared our results with literature. So our model turned out to have an accuracy of almost 96%. So then we implement this surface roughness model back to the cost optimization problem as one of the constraints. So as the case study in the cost part, we compared 3 production scenarios. The first one is non-mixed production with low machine capacity, meaning we just use a very low portion of the build platform. The second one is non-mixed production, but with a high machine capacity. And the third one is a mixed production. But with 3 different production layouts, we always make sure we achieve the same production yield, meaning we print the same number of parts. So basically, with the mixed production, we were able to save the yearly production cost from 6% to almost 16%. And that means production cost can be reduced just by adjusting your production layouts. So next we look at the optimization problem. And so we focused on this specific mixed production layout. We have different like engineering parts, different sides of schools, different engineering parts, like one of them is also for aerospace. And we have 15 of them. And we have a surface roughness requirement and a productivity requirement, and we solve the optimization problem. So we were able to achieve around almost 25% cost reduction without sacrificing the fabrication quality. Because you see the surface roughness of the optimized case still satisfy our requirement, which is less than 3.81 micrometer. So that's really exciting news because it basically means there are some opportunities here to save cost. Like before, you can change the production layout, right? So now you can change the values of parameters, and this model can make sure you still have the desired quality. So next, we also performed sensitivity analysis, and we found out that the material unit price is actually the key cost driver affecting the optimized cost and also the total yearly cost. Well, the next question here is, yes, we can reduce cost while maintaining the quality and production, but what about mechanical property, right? What about when we actually use this technology in our supply chain? Well, we actually did a lot more studies on these topics, but because of the time, I will not be able to share. But if you're interested, you can go on our website, Sigma Lab, to check out our publications and research studies. Now, the smart materials and green manufacturing are just two examples of many future research directions in 3D printing. There are so many other directions like 4D printing, large-scale printing, continuous printing, composite printing, waste recycling, remanufacturing, repair, and hybrid manufacturing. This is actually from one of my previous projects on hybrid manufacturing, where we use a robot arm to integrate both additive tools and subtractive tools. So yeah, that's all we have prepared for today's presentation. Dr. Ameri and I would like to thank you all for attending our Brown Bag series talk, and we are more than happy to answer any questions that you may have. Well, if we don't have enough time to answer all the questions, you can always reach us through emails. We have our email address listed here. Thank you.
Thank you very much for the presentations, both speakers. We really enjoyed knowing a lot about 3D manufacturing and how it can be made more environmentally sustainable, as well as some of the technical challenges of getting some of this work to do interesting manufacturing of components. So at this point, I'm going to open the floor to the audience for any questions that they may have. So while I'm looking up the questions that are there in the chat box, I wanted to start off things with a question of my own. So, I mean, one of the questions I was always wondering is, like, is there a limitation to the kind of geometry that you can produce with 3D manufacturing? And the same question for subtractive manufacturing. I mean, can you create anything, or are there some mathematical limitations to the kind of geometry that you can create?
Do you want me to start?
Please, anybody who is wants to take a crack at that.
Yeah. Thank you so much for the question. Yeah, so you asked about one of the edge of, we can say that it's the state of the art in the additive manufacturing. There are always demand for capability of fabrication of bigger size component in additive manufacturing. So far, the biggest size part that we can fabricate is about something around, I think that it's one of the GE machine that it's capable of have a part with height, with the length of 85 centimeter to 90 centimeter, as well as about 1 meter in height. So this is the biggest 3D printer part that we are capable of fabrication out of metals. But for the plastic, I observed, I saw several videos that is show the capability of fabrication of a big boat. Those actually it's fabricated in 4 or 5 days, I think that it finished. And as also Dr. Yang shows us the capability for the other material than the metals, we can even fabricate houses. Regarding the size, in the small size, the smallest size that I saw for the metal, it's about the capability of having parts with the resolution of 0.1 millimeter in thickness. This is the minimum things that they can fabricate it in micro level additive manufacturing. By the way, there are some customized machine that they are capable of fabrication of even nano metal components. But something between this range, almost they can do it for many of alloys, such as the stainless steel, aluminum, but for many also the other alloys such as refractory steel, the quality is not acceptable. There's no problem for fabrication, but I'm in terms of size, but in terms of quality, it's not acceptable right now for industry.
Thank you very much. So just moving along, I'm just going to read out a question from the audience. So this is from Dr. Brian Huff. Question directed to Emma. Did you consider part orientation when looking at part build cost for mixed product production? Did you consider part strength as a measure of production quality?
Yes, actually, I didn't go over all the parameters that I changed, but the parameters include the layer thickness and part orientation. Because of course, part orientation, like if you print like vertically or horizontally, that's gonna affect your production cost, definitely, of course. And well, how you orientate the part is gonna affect your cost, but also the quality, the surface roughness, and the strength, as Dr. Huff mentioned. So yeah, actually after the cost study, we had a separate study on mechanical properties, including the tensile strength, and we also look at the hardness. So yeah, that's in a different study. I didn't include that in the presentation. But to answer his question, yes.
Okay, thank you very much.
Yes, of course.
One more question from Dr. Huff, and I think this is for Dr. Ameri. Can you provide examples of applications of SMAs, shape metal alloys, specifically applications that require 3D printing?
Yes, so the application, generally speaking, the application of this material, more specific, the super elastic one, is in biomedical application because it has nickel as well as titanium. Both of them, they are really good and biocompatible, and they are right now used as implant as well as considering the for some strength where we need some stress-induced implant that they are under the kind of harsh environment like a human body, so they can act with a minimum amount of toxicity as well as ion relief, these two elements. For the additive manufacturing right now, so we have several applications more specific for the clot removal. There is a kind of specific design in the biomedical application for clot removal in heart surgery that they use the stem of nickel titanium alloy, or even some previously it was magnesium, now they are switching to nickel titanium, so it's capable of change the shape as well as deform dramatically. So these are the applications for the 3D printed nickel titanium.
Okay. Yeah, so there are several questions in the queue and we're getting close to the hours, but I'm going to sign off with maybe one question from the audience. And this is a question, let's put it for both of you. If somebody wants to be involved in your research, how can they prepare for it and how can be a part of your research? So maybe Emma can go first, and maybe.
Yeah, well, I'm sure Dr. Ameri and I are on the same page. We always welcome more students, right, to involve in our research, and we have our email address here. So if you're interested, please send us an email, and we can set up a meeting and talk about research opportunities.
All right. So I think we are at the end of the hour. It's 1 o'clock. I'm sure there are lots of interesting questions that still remain unanswered. But everybody, you know how to reach our presenters today. Please feel to contact them by email later on, and I'm sure they'll be happy to answer any further questions that you have. Thank you both very much for a very exciting presentation today. I myself learned a lot of things. I always enjoy these bound bags on my own, and I hope everybody else too. So thank you very much. Have a great afternoon, everyone.
Thank you.
Thank you so much for the opportunity.